Welcome! Today we're going to learn about integration with trigonometric substitution. So when do we use trigonometric substitution? Well, if you look at our example in item 1, this is first of all a very good candidate. If you look at that radical in the denominator, it's in a specific form. The form is the same as you see in item 3, square root of u squared plus a squared. That form is usually a good choice for trigonometric substitution. However, I always tell my students, first try u substitution. If you can do that, that's always an easier and better choice. Unfortunately, that does not work in this example, so trig substitution is the way to go. Other forms you should look for are those of item 4 and item 5. Okay, so let's try to solve our particular example. So the key thing here is recognizing this form kind of looks a little similar to what you would typically see when you have a right triangle, and you can use the Pythagorean theorem to calculate your hypotenuse. So if you look at item 3, we put that radical we had in our particular problem and we made that the hypotenuse, and then it's relatively easy to figure out what the sides look like. The 4x is the square root of 16x squared, and the 2 is the square root of 4. And then using the Pythagorean theorem, you can figure out what that hypotenuse is, and it matches the particular radical in our problem. Now, why are we doing that? Well, we're going to use this triangle to eventually substitute using trig functions and substitute what we have in our original integral. And the integral is going to be integrating a trig function instead, but hopefully it'll be an easier integral. That's the whole idea, to make the integration easier. Now, you have to start somewhere. You have to create equations here in order to make the substitution. In this particular form, the form in item 2, I always suggest using the tangent of theta as your starting point. So how do we do that? Well, we use SOHCAHTOA rules. If you look at the triangle in item 3 and you want to calculate tangent, it's opposite over adjacent, 4x over 2. And that's what we have in item 4. This is going to be your starting point, where we eventually manipulate and come up with different equations that we're going to use to replace what we have in our original integral. So let's use our triangle now to make those substitutions. And again, starting with that equation we just did, and I have it here again in item 3. Now let's look at our integral. If you look at item 2, I have our integral. And in the denominator, the first thing I see is an x. So I have to substitute. In other words, I want to replace that x with some form of theta, some trig function. So go back to item 3. That's where we started with our first equation that we calculated on the last slide. And you can solve for x just manipulating that equation. So in item 4, we solve for x. And we notice it's 1/2 tangent of theta. So in our original integral, we're going to take the x out and we're going to replace it with 1/2 tangent of theta. What else do we want to replace? Well, we have a dx. Now let me tell you, that is the most common thing students forget, and that is they don't replace the dx. They replace everything else and they forget the dx. So don't forget that. So that's what we're going to do next. What is the dx? How do we figure out what to substitute there? Well, go back to the last equation we did, which was in item 4. We solve for x. When you solve for x, the dx follows very easily. All you have to do is to take the derivative of both sides of the equation in item 4. And so we get what we have in item 5. dx, in this case, is equal to 1/2 secant squared theta d theta. And that d theta is key. Remember, when we started with the dx, but when we integrate, we're going to want a d theta. So all of that is going to replace the dx in our original integral. Now the only thing left that we have not replaced is our radical, the radical square root of 16x squared plus 4. How do we do that? Well, this is where we want to go back to the triangle, use a little SOHCAHTOA rules, and come up with some way to use that in an equation. So if we go back to our triangle in 1, we know with SOHCAHTOA, we do know the cosine is the adjacent side over the hypotenuse. That means that the secant would be its reciprocal. So therefore the secant of theta is the square root of 16x squared plus 4 divided by 2. And we have that in item 6. I've written that out for you. Now, that's not exactly what I'm looking for, though, because I don't want, all I want is what's under that radical, okay? So in item 7, we're going to just have multiplied both sides of the equation in item 6 by 2. And so in item 7, now we are solved for the radical that we want to replace. And we're going to simply replace that with 2 times the secant of theta. So we start with the integral in 1, and then in 2, after we make all those substitutions we just spoke about, we have the integral in 2. Now you might look at that and go, well, wait a minute, that's way more complicated. I don't think I've helped myself here. But trust me, after we make a few simplifications here, you're going to see this is actually a pretty good integral. So if we go to item 3, we cancel the 1/2. We notice that we have one secant in the denominator and secant squared in the numerator, so we can then cancel one of those secants out. And then if we go to 4, we have our new equation. Well, it's looking better, but not quite there. So if we go to 5, what we have done here is instead of secant, we call that 1 over cosine. Instead of tangent, we have sine over cosine, and it's in the denominator, so we have to take its reciprocal, which is why we have cosine over sine. The cosines cancel. That leaves us with 1 over sine. Well, what's 1 over sine? It's simply cosecant. So we have a new equation in item 6, and that's actually not a bad integral because the integral of cosecant is something you can simply look up and solve, write it out that way. Oh, by the way, the 1/2, if you don't remember where that came from, go back to item 3, you'll see there is that 2 in the denominator. That was pulled out front of the integral sign, and that's where the 1/2 showed up. So let's integrate. As I said, you can, if you haven't memorized the integral of the cosecant, you can look it up, and in item 2, that is your integral. So now we're good, but we're not great because we still have to then switch back to x as our main variable. So this is where we go back to our triangle and we just do the opposite of what we did. We're going to replace the cosecant now with something in terms of x. Again, cosecant is 1 over the sine. Using SOHCAHTOA, sine is going to be your opposite over the hypotenuse, so in this case it would be the hypotenuse over the opposite. And that's what we have replaced cosecant with. Again, now we also have to replace cotangent. Cotangent is cosine over sine, or you could say it's the reciprocal of tangent. And in SOHCAHTOA, tangent is going to be opposite over adjacent. But this is cotangent, so it's adjacent over opposite. And that's 2 over 4x. So you make those replacements in item 3. Then in item 4, we find a common denominator, and we are good to go. That is our final answer. And that's how we integrate with trigonometric substitution. Now go practice, practice, and practice some more.